We have been covering um, Chapter 5, Sections 3 and 4, talking about some rules about adding and multiplying probabilities. So, I want to kind of cover, this lecture is going to recap the addition rule for probability, and I'm going to go over some problems that are in this section. So just to recap, when we talk about probability, we think of the set of, well, we think of our scenario first, and then we define a special type of set of all the possible outcomes in that scenario. And that set is called, all possible outcomes, right? Called the sample space. So this would be the sample space. We draw a rectangle for it. Then we think of an event, which is a subset of the sample space. So it's some smaller set of possibilities within the sample space. Okay, so let's say I'm talking about dealing cards, right? So my event A is the probability of getting a red card. So I would write A equals red card. Okay. So the way we define probability is we take the number of things in the event, and then we divide that by the number of things in the sample space. So we take the number of ways that we can get a red card, which half of the cards are red, so it's 26. And then we divide that by the total number of possible outcomes, which is 52. So this is 1/2. So half the time you're going to get a red card. This is what we're used to doing in probability. We're literally just dividing two numbers and assuming all the possibilities are equally likely. Getting red and black cards is equally likely. This is kind of a nice way of introducing probability. Let's consider now, to talk about the addition rule, let's consider another event B. Let's say we want to get getting a jack. Okay? Getting a jack. Well, the probability of getting a jack, there's one of each suit, as we've learned, so that's going to be 4 out of 52, or 1 out of 13. Now, what if I ask the question, alright, I want to get a jack or a red card. So now I have my circle of possibilities with a jack, and then I have my circle of possibilities of getting a red card. My sample space is getting any card. Okay, well, then my probability of getting a red card, we already learned, is 1/2. My probability of getting a jack is 1 out of 13. So this seems like it might be the answer. The problem is that if I were to literally deal out every card and say, okay, in this scenario, what are all my red cards? And I count up all my diamonds, and then I count up all my hearts, and I end up with 26, which is what I got here. If I count up all my jacks, then I would end up with 4. But the thing is, 2 of those jacks are red cards. So up here, I counted the jack of diamonds and the jack of hearts. And then down here, I'm going to also count the jack of diamonds and the jack of diamonds and the jack of hearts when I count up my 4 jacks. So I've counted the same cards twice, 2 of them, twice. So the 2 red cards that are also jacks have to be subtracted away. Right? And then we actually end up with our answer. So it'd be easier if I write everything with the same denominator. So there's 26 out of 52 plus 4 out of 52 minus 2 out of 52. So this turns out to be 28 out of 52, which reduces to 7 out of 13, I think. All right. Point is that you need to consider this overlap where both things can happen at the same time. So this formula, the addition rule, looks like this. Probability of A or B is the probability of A plus the probability of B minus the probability of A and B. This is called the addition rule. This is when you're considering this or that or both events happening. So let's say two events could not occur simultaneously. They could not happen at the same time. Let's say I said this is the probability of getting a spade, and this is the probability of getting a red card. Okay. Well, the probability of getting a spade that is also red, assuming you have a normal deck, is the number of ways that I can get a red spade over, the total number of possibilities. But the number of ways of getting a red spade is 0. There's no red spades. So I have my spade circle, and then I have my red card circle, and there's no overlap between the two. So when this happens, when there's no overlap, we call this mutually exclusive. Right? You cannot find a card that would fit into both categories at the same time. So our formula becomes a little easier. The probability of A or B, notice the difference here. This is and this is or. That's important. So the probability of A or B is going to be the probability of A plus the probability of B. And we could still write the probability of A and B. The only thing is that now this is 0. So it just becomes the sum of the two. Alright, so it's easier to deal with. So this is a consequence of being mutually exclusive. You want to see what the probability of both of them happening is, just add them together. So in this example, the probability of getting a spade is 13 out of 52. The probability of getting a red card is 26 out of 52. So now we just add them up and we get 39 out of 52. Okay? Great. So let's run through an example real quick. Example 520. A single card is drawn from a deck. Find the probability that it is a king or a club. So the probability of being a king or a club. Alright, so let's write our formula. Probability of A plus the probability of B minus the probability of both happening at the same time. Well, the probability of being a king, how many kings are there? There's 4. So that's 4 out of 52. The probability of being a club, there's 4. There's 13. How many kings are there that are clubs? So there's 1 king of clubs, so we subtract it away. And we get 16 out of 52. Alright. So that's pretty much it about this rule. So you just need to remember the idea behind mutually exclusive right there, meaning that there's no overlap. And think about, is the event that I'm talking about of having this or this happen, is that is there any overlap in those two circles? If there is an overlap, then you have to subtract something away, like here, where I can get a red card that is also a jack. Here, there's no overlap because you can't get a spade that's also red because the spades are all black. All right? So here's your homework assignment, pages 186 through 188, numbers 38 through 64. Even. And they're all pretty easy, just basically learning the different ways that you use that rule. So I'm going to do a few. I'm going to do the odds. 5, 39. So give an example of two events that are mutually exclusive and the two events that are not mutually exclusive. So two events that are mutually exclusive, we already did one. Getting a red spade. You cannot get a card that is red and also a spade in a normal deck of cards. Two events that are mutually exclusive. How about getting heads and tails in one coin flip? Not going to happen, right? Not with a regular coin. Okay, two events that are not mutually exclusive. Getting a red king. Rolling a 6 or even number, right? So rolling a 6 or an even number. A 6 is an even number, so they're not mutually exclusive. Okay, so that's the idea behind that. 541. A furniture store decides to select a month for its annual sale. Find the probability that it will be April or May. Assume that all months have an equal probability of being selected. So a furniture store is just randomly picking any month of the year, and we want to know what the odds are that they're going to pick April or May. Well, we write our formula. Probability of April plus the probability of May minus the probability that they would pick both at the same time. That's what this "and" means, is they're both happening at the same time. But if you're selecting a month out of the year on your calendar, there's no way to select two different months at the same time, right? So this is 0. So you just end up saying, well, the probability of getting April or May for the selected month is just the probability of getting April, which is 1 out of 12, plus the probability of getting May. So it's 2 out of 12, which is 1/6. At a convention, there are 7 mathematics instructors, 5 computer science instructors, 3 statistics instructors, and 4 science instructors. If an instructor is selected, find the probability of getting a science instructor or a math instructor. So same idea. We have 7 math. We have 5 computer science. We have 3 statistics. We have 4 science. If an instructor is selected, find the probability of getting someone who is a science instructor or a math instructor. So probability of science plus probability of math minus probability of science and math. And it's safe to assume here that you can't have somebody, since they haven't said anything, that you don't have any guys who are teaching both. So that means this is 0. So the probability of getting a science instructor is going to be 4 out of the sum, 7, 14, 19. Right? The sum of everything, I mean. Plus the probability of getting a math instructor is going to be 7 out of 19. So it's 11 out of 19. On a small college campus, there are 5 English professors, 4 mathematics professors, 2 science professors, 3 psychology professors, and 3 history professors. If a professor is selected at random, find the probability that the professor is the following. So, 5 English, 4 math, 3 psychology, 3 history. Okay. So part A says the probability that you get an English or a psychology. Well, there's a total of, you count the total, 5 plus 4 plus 3 plus 3, 6, 10, 15. So there's probability of English or psych is going to be 5 English out of 6 and 10 is 15. 5 out of 15 or plus 3 out of 15, which is going to be 8 out of 15. Okay? So there's no overlap in these problems. So these are all mutually exclusive problems that we've dealt with so far. So B, C, and D, again, you're just going to think of the numbers that you have here and just add them up without worrying about subtracting anything. So B says a mathematics or science professor. So just look at math. That's 4. And then a science. Oh, I forgot to write science. 2 science. 2 out of 15 is equal to 7 out of 15, right? And then C, history, science, or math. So history is 3 out of 15. Science is 2 out of 15. And then math is 4 out of 15. This is 5, 9 out of 15. So reduce, divided by 3, 3 out of 5. Okay? That's basically all there is to that. Let's see. Let's do 5-53. Something a little different. A grocery store employs cashiers, stock clerks, and deli personnel. The distribution of employees according to marital status is shown. So they have marital status. Married or not. Married. And then you have the cashiers. We have the stock clerks. We have the deli personnel. Right? 8 out of 5. Okay. The employee is a stock clerk or married. See, so now there's an overlap here with this table. So what's the probability of being a stock clerk or married? Well, you could be a stock clerk. So first of all, we want to count up the totals here. So there's a 13, 27, and 5. 18 and 27 is 37, 43? 40, do I know how to add here? 37, 45, sorry. 45 total. Okay, so stock clerk or married. So the total number of stock clerks is 27. So probability of stock or married is going to be 27 out of 45. So how many people are married? Well, you add these numbers, 8, 12, and 3, that's 23. But then, is it possible to be a stock clerk and married at the same time? Absolutely, right there. So that's 12 out of 45. And I double counted because I counted up all the stock clerks and I got 27, but 12 of those stock clerks were also married. I counted up all the married people, but 12 of those married people were also stock clerks. So I counted those people twice. And now I subtract them away and I get 11 from here, so that's going to be 38 out of 45. That's my answer there. And that's basically how you do the homework. You just use this rule, think about the scenario, and that's pretty much it. So, good luck. Let me know if you have any questions.